Hi everyone, welcome to our video lecture on section 3.1 dealing with the introduction of the derivative. In this set of videos, we're going to be discussing average rate of change and how they can become instantaneous rates of change, and then we're going to be discussing the concept of the derivative. Now, the concepts of average rate of change and instantaneous rate of change are nothing new. In section 2.1, we explore the differences between them. However, now that we have more tools under our belt, we will be revisiting these ideas. Alright, so let's recall that the definition for an average rate of change was the following. The average rate of change for a function f on the closed interval from a to b was given by the formula f of b minus f of a all over b minus a. Now recall that this one was just the slope of the secant line going through the points a comma f of b and b comma f of b. In section 2.1, we use this formula to find the average rate of change for the function f of x equals to x squared plus 2 on a bunch of different intervals. So let's recall these intervals. The average rate of change between 1 and 2 was 3. Then the average rate of change between 1 and 1.5 was a 2.5. The average rate of change between 1 and 1.1 was 2.1. And the average rate of change between 1 and 1.01 was 2.01. Now, if I were to ask you, hey, which slope best approximates the slope of f of x, the function x squared plus 2, at an x value of 1, and remember the trick that we were using here was to basically select smaller and smaller intervals between a and b. So it seems like the smaller the distance between our intervals a and b, our slope was getting closer and closer to 2. So I would say here that the slope of f of x at x equals to 1 is equals to a 2. Now remember, if you're interested in finding the slope at only one particular x value, then what we're basically looking for was the slope of the tangent line, which was the exact same thing as the instantaneous rate of change. Alright, now, here's what I want you to think about. Can we determine an expression that will allow us to calculate the exact slope of f of x at x equals to 1? Because we already know that the slope was 2, but the way that we got the slope was by essentially selecting smaller and smaller intervals between our x values and then see, okay, what value did you seem to be approaching? But is there a formula for it? Well, I'm going to give you guys a hint here. Well, 2 hints actually. Now remember that the slope for a secant, which I'll put here as m secant equals to f of b minus f of a all over b minus a. All right, perfect. So we were using this formula here with these intervals to approximate the slope of the tangent. But can we get a formula? Can we maybe use the equation for the slope of the secant line to help us? Because this is my other hint. When we were using this formula, what value in the intervals was changing? Well, notice that the 1 always remained fixed. So in this case, the a didn't really change, but what was changing was the value for the second one. Now notice that the right endpoint was the one that was changing, and well, it seemed to be approaching the value of 1. Now because this was the interval that was changing, it was variable, I'll call it f of x. So what we were doing here really with the equation for the slope of the secant was doing this evaluation, f of some x minus f of 1 all over x minus 1. So with these 2 hints here, it's like, okay, we've used the equation for the slope of a secant, and the right endpoint was the one that was changing, but it was approximating the value of 1. So, can we use that and come up with an expression or a formula that will give us the slope of a tangent line? Alright, so I'll let you pause the video, think a little bit about this one here. What can we do? And then we'll see if some of your formulas match mine. Alright, so let's pause the video here. Well, if you heard me use the word approaching quite a bit and thought about limits, then you'd be correct. We can actually modify the equation for the slope of a secant and turn it into the equation for the slope of a tangent with the use of limits. So in this case, when we were taking a look at the approximation for the slope of f of x at x equals to 1, Yes, our x values were getting closer and closer to 1. So this one here was the equation that I got. The slope for the tangent is equals to the limit as x approaches 1 for f of x minus f of 1 all over x minus 1. So now let's take a look at a new definition. In this case, it's going to be the definition for the slope of a tangent line. Now, the tangent line to the curve y equals to f of x at a point P given by a comma f of a is a line through P that has the slope given by the limit as x approaches a for f of x minus f of a all over x minus a. And again, I want you to remember that the slope of the tangent line is the same as the instantaneous rate of change. Now, we sometimes refer to the slope of the tangent line to a curve at a point as the slope of the curve at a point. We don't always just need to include tangent line because it's implied. All right, now with this new formula, can we calculate the slope of the tangent line for the function f of x equals to x squared plus 2 at x equals to 1? All right, so let's take a look. Since we're looking for the slope of the tangent line at x equals to 1, basically our a value is equals to 1, so then we're going to be taking the limit as x approaches 1 for f of x minus f of 1 all over x minus 1. All right, so plugging everything here into the function, and again, don't forget the limits. We obtain the limit as x approaches 1 for x squared plus 2 minus, open parentheses, 1 squared plus 2 all over x minus 1. Now we can go ahead and simplify this one here to obtain the limit as x approaches 1 for x squared minus 1 all over x minus 1. Now with this one here, we can see that if we go ahead and use direct substitution, then we would be getting 0 over 0, which means that we can do more work, but it's good because I believe we've done this problem quite a bit. So now I'm just going to go ahead and factor in a limit value of 2, just as we expected. But now we did not need to do multiple calculations or do a table of values. No, we just go ahead and evaluate the limit, and we get the slope of the tangent line. Excellent. Now, here's the thing, though. What if I told you, hey, you know what, guys? I actually made a mistake. I did not want you to figure out the slope of the tangent line at x equals to 1. I actually meant to say the slope of the tangent line at, let's say, x equals to, I don't know, a negative 3. Now, what would happen here? Well, that would mean that we would need to go ahead and repeat all of this procedure again for the new value for x. Now, what if I said, oh, you know what? It actually wasn't negative 3. It was, hey, find me the slope of the tangent line at x equals to 5. We would have to do the whole process again. So you see here that even though this method is very nice, it does give us the slope of the tangent line. If we wanted to select different tangent lines, though, it does become a tedious process. So now I want to talk about a second, and what I would consider a better approach. All right, so let's go ahead and take a look at this graph here. Now this is actually the graph for f of x equals to x squared plus 2, so I'm going to go ahead and label it here. Now I'm going to go ahead and label the coordinates for the 2 points that are marked. So this point here, I'm going to say that it is happening at some x value equals to a. So this means then that our function value right here is f of a. Okay, perfect. Now this is what I'm going to do now. Rather than defining this new point here at, let's say, x equals to b or some other value, well, instead here is I'll focus on the distance between a and this new point. And I'm going to say that this distance is a distance of h. So if I want to go from a up until this new point, and I know that I'm covering a distance h, then the coordinates for this point right here are a plus h. Okay, well now if I'm selecting the input to be a plus h, then our output, the function value here, is going to be f of a plus h. Okay, now notice that we do have the curve here, the quadratic in black, but there's also a secant line here in red. So with this new information, the actual coordinates for the points, I'm going to go ahead and write down the slope of the secant line. So here we have the slope of the secant line, and we get to see immediately that in our denominator, it seems like the a's cancel. All right, perfect. So it seems like the slope of the secant here is given by f of a plus h minus f of a all over h. All right, perfect. So now that we have the slope for the secant line, how can we obtain the slope of the tangent line? Well, based on the previous problems, the way that we obtained the slope for the tangent was by letting the intervals in the axis here get smaller and smaller. So I'm going to go ahead and repeat that process here. I'm going to go ahead and let the intervals in the axis get smaller and smaller, but that is another way of saying that I'm going to let this distance h be smaller and smaller. So for example, I can go ahead and pick a distance that's about half of the original h, somewhere around here. Now this is going to give me a new point on the curve, and I could go ahead and create secant lines, but it's still going to be a secant line. But if I go ahead and pick smaller and smaller h values, well, then you get to see here that at some point our secant lines would start to resemble tangent lines. I could pick an even smaller h here, and like, okay, yeah, it does seem to be getting closer and closer to a tangent line. All right, so in this case, the way that we can obtain the slope of the tangent line is by modifying our secant slope formula by adding a limit, but this time around, the limit is the limit as h, the distance in the axis, go to 0 for f of a plus h minus f of a all over h. And this is our equation for the slope of the tangent line in a different form. Now, to be honest, guys, this is the way that I'm going to ask you to remember it. It's a lot more useful because when I gave you the previous problem, I told you that if you chose a different x, you would have to repeat the factoring process over again. But if we kept it here in terms of h instead of any other point a, you only need to do the calculation once, as we'll see in a couple of examples. All right, now, without further ado, now let's take a look at a new definition, and this is now the definition for the derivative. And here we have it in all of its glory. For a function defined as y equals to f of x, its derivative at a point x equals to a is the function. Now we have an f, but what seems to be an apostrophe here. This is read as f prime at a. And this is defined by the following formula. F prime at a is equals to the limit as h approaches 0 for f of a plus h minus f of a all over h, provided of course that the limit does exist. Now I want you to highlight this. This is known as the limit definition of the derivative. Remember that, because in some problems I'll ask you to use this specific definition. Alright, so now that we heard the word here, derivative, what does it mean? Well, you got to notice that, hey, the formula is just the slope of the tangent line, and that is what the derivative is. The derivative is simply the slope of the tangent line, which is the same thing as the instantaneous rate of change at a particular point x equals to a. Now, if f prime of x exists, then we say that f is differentiable at x. In other words, if the derivative exists, then you can calculate the instantaneous rate of change at any point in the function, well, assuming it's differentiable for all x. Okay, so now let's go ahead and put our derivative formula into practice by taking a look at this function. Let's see if we can go ahead and figure out what is the derivative of the function f of x equals to 3x squared at x equals to 1, and then let's see if we can find the equation for the tangent line at x equals to 1. This is going to be a very typical exam problem. I'll give you a function, I'll ask you to find the derivative, and the equation for the tangent line. So let's go ahead and get some practice. Alright, so let's find the derivative f prime of a. Okay, now we're going to go ahead and use our limit definition. We know that f prime of a is equals to the limit as h approaches 0 for f of a plus h minus f of a all over h. Alright, so since we're looking for the derivative at x equals to 1, our a value at some point is going to be equals to 1. But when you're working on this type of problems, what I want you to do is keep the most general formula for the derivative. So what I mean by that here is simplify the limit, but keeping the a intact. Towards the end, once you simplify it enough, or as much as you can, then we're going to be letting the a value be equals to 1. But in the meantime, I want you to just keep the a's. Because again, I'm looking for the most general formula for the derivative, not at specific a values. Okay, so keeping the a as a variable, let's go ahead and simplify our limit. So we're going to get here f prime at a is going to be equals to the limit as h approaches 0 for 3 times a plus h squared minus 3a squared all over h. Alrighty, now you might have noticed here that if you actually plug in the h value of 0, we do get an indeterminate form. We would have gotten a 0 over 0, which meant that, yes, we do need to do more work. And that's going to be the case for a lot of these problems. If you plug in the h value of 0 at the very beginning, it's not going to work. So let's go ahead and simplify this one out here. See if we can maybe cancel things out, maybe factor. Let's take a look. In this case, it doesn't seem apparent that I can factor, but because I do have a power of 2 here, then I can probably expand. So let's take a look. Expanding it out here, we're obtaining the limit as h goes to 0 for 3 times a plus h minus 3 squared all over h. Now again, just to clarify it here, this first part was the f of a plus h minus, and don't forget to include parentheses whenever you're subtracting another function. This one here was our f of a. Okay, so following everything out here, let's see what we would get. You guys can go ahead and verify it, but I obtain the limit as h approaches 0 for 3 times a squared plus 6 times ah plus 3h squared minus 3a squared all over h. And good news, I do see things that cancel. The 3a squared cancels with negative 3a squared. And what else can we do? Well, I can go ahead and factor h from the top, which is now going to give us the limit as h approaches 0 for h times 6a plus h all over h. Now, beautiful, beautiful, we can cancel the h's here. And now, using direct substitution, well, I'll do one more step here, because this is different than what we've done before. Normally, when I ask you to simplify limits, well, actually, I guess it is not all that different. But I will write that extra step here. But here, the limit as h goes to 0 for 6a plus h. And since h is going to 0, our final answer here is the 6a. This is the derivative evaluated at any a. This is what I want you to obtain. Because now, doesn't matter what a I give you, you know what the derivative will be. The derivative will simply be 6 times a. In other words, this is telling us the slope of the tangent line at x equals to a. Alright, so for this problem then, if we were interested in figuring out, hey, what is the derivative evaluated at 1? Well, now we have the formula that tells us the derivative at 1. It's simply going to be 6 times, and in fact, let me put in a different color. Put this one here as f prime at 1. Put this one here in green. And it's just going to be equals to a 6. Alright, so this is telling us that the slope of the tangent line when x is equals to 1. If I instead was looking for the slope of the tangent line when x is equals to 2, well then, we would just multiply 6 times 2, which would give us a 12. Okay, now this is not the end of the problem though, because I also want you to write down an equation for the tangent line at x equals to 1. So I want to remind you of the equation for a line. This is the equation for a line in point-slope form. You might remember it here from a previous calc course or a pre-calc course. We're going to have y minus y1, which is equals to the slope times x minus x1. Now, you might remember this form of the equation, but this is not entirely the one that we're going to be using in class. It's the same formula, but represented differently using function notation. So this is the way that I want you to remember it. Y, okay, switching to function notation, this is just going to be an f of x minus y1. Well, the y1 is simply the function value evaluated at x1, or maybe a, if you want to call that the x. And key distinction here, what is the slope? Well, since we're looking specifically for the equation of a tangent line, then the slope is simply the derivative evaluated at a given x value. So the slope is now going to be f prime of x1 times x minus x1. Now you can go ahead and replace the x1s with the a's if you want, but this is the formula that you definitely need to remember. I guarantee it. You're going to be seeing it in the exam and through the rest of the class. Okay, so now that we have the equation for a line, let's go ahead and fill in the necessary information. So for this problem, we're going to have an f of x minus f of x1. Well, you might remember that the function here was 3x squared. So if I ask you, okay, well, since I'm looking for the equation for a tangent line when the x value is 1, let's figure out what is f of 1. So with f of 1, we obtain right here simply a 3. The 3 times 1 squared, if you want to put it that way. Okay, so now we have our f of x1, and this one here is going to be equals to the slope. Now, what was the slope at x equals to 1? We got a slope of 6 times x minus 1. In fact, let me change the color here for the slope. There we go. And that's it. Now, I don't require you guys to isolate the f of x. You can just leave it as is. This works just fine. Or if you wanted to give me a y minus 3, yada, 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 that's also fine. Yeah, I'll leave it like this. Okay. Now, let me just include here. We're done. All right, so this concludes part 1 on our video lecture for section 3.1, dealing with the introduction of the derivative. As we've seen right now, the derivative is simply the slope of the tangent line or the instantaneous rate of change. So in part 2 for this video lecture, we're going to be focusing more on problems involving the derivative. See you there.